Let's learn about root mean square voltage now, also known as VRMS. What is average power and how do we calculate it for an AC circuit? Now remember your RMS, your VRMS, it's an equivalent voltage which represents the DC voltage value that will produce the same heating effect or power dissipation in a circuit. Now what does that mean? Imagine that you have two electrical systems. Say you have this AC system right here, okay? You also have a DC system here. In a DC system, you have a DC battery over here. This is a positive terminal, this is a negative terminal of the battery, and you have some resistive load here, which could be anything, a bulb, fan, or motor. Now, if you are going to plot a DC voltage or current or power for that matter, because the DC potential is basically a straight line, it's so easy to find power at any instantaneous time. So let's say, for a DC voltage to be represented on a scale of X and Y, where X, say you have time here, okay, say in seconds, and then you have voltage over here. Okay, actually this could be just a magnitude. Okay, so this is just some magnitude over here. Okay, so DC potential would just be a straight line like this. Okay, and we would refer this to as VDC. I'm not going to assign any value to it. Similarly, if I look at the current, the DC current that's flowing in this circuit over here, okay, that would be just a straight line like this. Okay, say it is some value, I'm gonna just say IDC, the DC current over here. And if I am going to calculate the power, I know that power is a function of current and voltage. Therefore, if I multiply the current and voltage, I'll get something like this. And again, this will be a straight line, which will basically represents the DC power in this given circuit right here, right? Okay, now notice here over a period of time, the power, voltage, and current all remain same, and that's because of the nature of the DC circuit where the potential remains constant, right? Now let's move on to the AC system. Okay, imagine that you have some load over here. You have the AC signal coming in. You also are going to plot the voltage, current, and power. And remember, you can also assume that this resistive load right here and the one over here is same, and therefore you would think equal amount of power would be dissipated. But the problem here is the AC signal is sinusoidal in nature, which means it's basically swinging, right? You have the positive half wave, then you have the, I'm actually gonna change the color here, and I'm gonna, yeah, so this is my AC voltage for positive half wave, and then you have the negative half wave here. Okay, so it peaks about somewhere over here, somewhere over here, right? So I'm gonna say this is my peak voltage over here. Okay, and this is the negative peak right here, so I'm gonna say this is Vn. Okay, and again, remember, on the x-axis you have the time in second. Similarly, if I'm going to plot the AC current, because of the resistive load here, the voltage and current are going to be in the same phase. It's just the magnitude might be a little different. Okay, so say in the red, this is your current over here. Okay, now let's calculate the power. Again, we know that power is a function of current and voltage, and at any given instantaneous time, say if I want to measure the time period at this time scale over here, so I'm looking at the current, which is over here, and then voltage over here. So my power is going to be the product of these two data points, correct? So if I plot power for it will be something like this, and once it gets to 0, remember because both current and voltage are in negative, so negative negative will cancel out, and then you'll still have this same wave like you have over here, something like this. So okay, so that's your power. Remember, your green is your power over here. You have your red, which is the current, and then the blue represents the voltage here. Okay, so that's a classic difference between an AC signal right here on the left, and then you have the DC signal on the right. Now the problem over here with the power, at every instantaneous time the power is different. So power is different at this time, the power is different at this time, and power is different at this time over here. There has to be a way for us to find out an average power which is equivalent to this DC power in this circuit over here. Okay, all right, and therefore we need to find out an RMS voltage, which is equivalent voltage, which represents a DC voltage value for an AC system. Okay, so how do we find that VRMS? Okay, just to give you an equation, there's a way to calculate VRMS, and that equation is VRMS equals to the peak voltage VP over under root 2. Okay, all right, or in other words, this equation can also be written as VRMS equals to V peak times 0.707. Okay, also some books may say that V peak might be written as V max. So both are same thing, and remember you have the 0.707. Basically, if you take 1 over under root 2, you get 0.70. Okay, so that VRMS is going to be the constant average value for an AC signal in the given AC system, which you are going to use to calculate the average power, V square over R. Here V will be the RMS value over here. Okay, and this average power that you calculate is going to be the equivalent of this DC power in a DC circuit where the potential is just constant. Okay, so that's a basic background, why we need RMS voltage, what exactly it is, and how do we calculate an average power. You might also want to learn about something which is also known as the instantaneous power. Okay, what instantaneous power is, if you look at it, if you are going to calculate the power at this time, which is going to be the product of these two data points, or say over here, the power is going to be the dot product of these two over here, and I'll say this is my P1, go back, yeah, and I'll say this is my P1 and this is my P2. P1 and P2 could be referred to as the instantaneous power. Okay, and usually power is represented in watts. Okay, and what they really mean is you are calculating power on a given time for an AC system. Now let's move on to the finding ways on how to calculate the VRMS. Okay, so there are two ways of doing it. One of the ways is the graphical method, as you can see over here. What is the graphical method? This method can be used to find out the RMS value of any sinusoidal time varying waveform by drawing a number of mid ordinates onto the waveform. What does that mean? Okay, what I'm going to do is actually draw the positive half wave of the sinusoidal signal. Okay, so say this starts from here. Let me change the color actually. So say, yeah, it's going to reach its maximum value over here, and then goes like this and reaches negative value over here. Okay, but I just want you to focus on the positive, okay, wave over here, which is this right here, the positive half wave. And then remember, this is the negative part right here. Also, you can represent the x-axis in time and also in an angle, okay, which is represented by theta, and in the previous plot we had the seconds over here. Okay, now usually voltage in a resistive load will reach its peak value around 90 degrees. In radian we would say pi over 2. The positive half wave will complete its half cycle around 180 degrees, which we know as pi, and then you have 270 degrees, and then one complete rotation, which is positive half wave and negative half wave, that is 360 degrees, which is equivalent to 2 pi. Okay, now there are three steps. Imagine that we have this AC signal right here, and then we are trying to, for this AC signal, we are trying to find out the VRMS, the constant potential, that VRMS thing, which is going to be equivalent of any DC potential in a given circuit. Okay, now, so, and also it's given over here that the peak voltage is 20 volt. So say this voltage over here is, which is a peak voltage, and it's actually 20 volts, okay, which would also mean that this negative voltage over here is going to be negative 20 volts. But remember, we're not really concerned about that negative part. We're only focusing on the positive half wave. One of the things that you have to do, you have to split and make segments of equal spacing in the positive half wave of the signal. Okay, basically splitting it into equal distances. So say, if I make 1 2 3 4 5 6 7 8 9 and then say you have 10 over here. Okay, so these are equal spacing. I did my best making sure we have equal distances over here. Okay, and then remember, each of these corresponds to a certain angle, right? So if you're looking at this angle right here, okay, at this angle it represents a certain voltage here, right? So over here around 45 degrees it will represent some voltage over here, correct? And similarly 0 over here, and then so on, correct? So since I have actually broken it down into 10 segments, where say this is my V1, this is my V2, V3, V4, V5, V6, V7, V8, V9, and this is V10 right here. Okay, so now I'm going to move on to going into implementing these 3 steps right here to calculate the VRMS. And also, I also want you to tell you here that because I have broken it down into segments in 10 equal space segments here, I'm not gonna draw the whole thing right here. So because this whole thing represents this whole thing here represents pi, right? Pi right here. This is 180 degree, right? One complete positive half wave is basically pi. So the total length here that we are looking at, total length is equal to pi, okay? And the resolution here, or the spacing, and maybe I can say resolution here, is equals to 180 degrees. I can also say 180 degrees here, 180 degrees over 10, right? So this will come down to 18 degrees. Means every 18 degree I am taking a reading, voltage reading. Every 18 degree after I take 10 readings, I basically get to 180 degrees. Okay, now I went ahead and collect some data from some source, and say at V1, which would be 18 degrees, right? So 18 degrees, this represents V1, which was 6.2 volts. Okay, these are all the voltages and these are all the angles, correct? So the next time it's going to take the reading will be 18 degree plus 18 degree, which will be 36 degree. The reading is 11.8 volts, V2. Similarly, this is my V3, V4, it goes all the way, and my V10, which is basically 180 degrees, the voltage is touching the x-axis 0, so this will be 0 volts over here. Okay, now what is next? The first step is to take the squares. Taking square, VRMS equals to, the first step is taking square. What we need to take squares, and I'm going to put in an expression form. Okay, so V1 square, V2 square, V3 square, and then all the way it will go to V9 and then V10 square. Okay, all right, cool. What is the next step? Next step is to take the mean of all these squares. So I'm going to add all these values, okay, all these values, and then divide it by what? Because I have 10 readings, so I am going to divide it by 10, okay, because I have broken it down into equal spaced 10 segments. And then the third step is to take the square root. Okay, square root of this whole thing. That's what VRMS means. Root means square value of the AC signal. Now, if I plug in the values here, okay, and I'm not gonna do the whole thing. So V1 was how much? 6.2 square plus 11.8 square plus 16.2 square. And then similarly, we do it for the rest. V9 is 6.2 square. And then V10 is 0 volts, so 0 square, divided by 10. And if you do the math here, you basically get what? You get 2000 over 10. This 0 will cancel out with this. Then you're left with 200. And if you take a square root of that, you get 14.14 volts. Okay, so what does this 14.14 represents over here? This is going to be the average voltage, which will be somewhere over here. Okay, all right. Now if I, for this AC signal, so say, you know, we had this circuit, resistive load, and we had a peak voltage which was VP 20 volts. Okay, if you have this 20 volt peak voltage given, from there you can calculate the VRMS, right? We only had peak here, and then from there we did the, you just have to decide how many segments you will break it down into. I took 10 segments, you know, which was the resolution in my case. But remember, if you take 20 segments, you'll get more precise readings. Okay, and then for this we got 14.14 volt VRMS, which was 14.14 volts. Okay, now I can calculate the average power of this AC circuit by using this equation, V square over R, where V represents the RMS value and R will be this value right here, and that's equivalent to the power that you will get for a DC circuit, right? So that's one of the ways of and it's referred to as the graphical method to calculate the VRMS value. Now the other method is requires some extensive amount of calculus and trigonometric function background, so I'll try to explain as much as I can, but I want you to focus over here. Now, analytical method to calculate VRMS. For a pure sinusoidal waveform, you know, we can make life a little bit easier for ourselves by using an analytical or mathematical way of finding the RMS value. I just want to go back here and want to explain over here. This graphical method could actually be implemented to any kind of alternating waveform. Okay, you just need to make sure that you split it into equal space segments, and then you follow this process right here. In case of the absolutely pure sinusoidal 60 hertz frequency positive wave reaching its peak value at 90 degrees, a pure sinusoidal waveform, we can use this analytical method, and it's not that difficult. It's just have a lot more, you know, work process into it. And I'm going to put this value right here again for the VRMS. Again, VRMS equals to VP over under root 2. And when I first put that equation earlier, you might be wondering, where did I get this V under root 2? Okay, also remember this V peak value is actually also equals to V max. Okay, they are basically same thing, it's just different terminologies may be used. Now, a periodic sinusoidal voltage is constant and can be defined as a function of V max cosine omega t with limits taken from 0 degrees to 360 degrees or t. Okay, remember folks, when you are looking at the sine wave, okay, the sine wave, the time it takes to complete one oscillation or one complete cycle is referred to as t, where this is pi and this is over 2 pi. 2 pi would mean 360 degrees, correct? Okay, now we're gonna do the first thing we're gonna do, the same steps we are going to follow like we did in the previous method, is just I'm going to rewrite the signal over here. The sine signal is represented in a time domain which equals V max or V peak. Okay, let me just say VP, yeah, let's say VP. Okay, it's the peak value times cosine of omega t. Okay, now again remember omega is the angular frequency, which is equivalent to 2 pi f. Okay, f equals to 1 over t, correct? So frequency is going to be 1 over t, where t is the time it takes to complete the cycle. If I put this f here in this equation, I can also write omega equals to 2 pi over t. Okay, so just keep this in mind and just try to follow along with me. So the first thing I need to do is take the square. Okay, all right, let's take the square. So I get what? V square peak value square, okay, dot cosine square of omega t. Okay, all right, that's cool. Now let's move on to the second step. The second step is to take the mean, where we are going to add all the square values. Okay, and we are looking at what? We are looking at this, which is the total length is how much? T. Okay, so remember, taking mean over here, we are taking all these values. Let me go back. Taking all these values at different intervals, squaring them, and taking a mean of it over this period right here. So that is equivalent to taking an integral, correct? With limits from 0 to t, and then this will be d of t. Okay, again, we are doing this in reference with time. The third step here is to take the square root. Okay, so this VRMS is equals to this right here, this whole thing. Okay, and I'm just gonna so this right here is your equation to get the VRMS, okay, for a perfect sinusoidal signal. Now I'm gonna actually convert this to something like this. Okay, and you'll see how I do that. Okay, now for the sake of the explanation and easiness, I'm gonna take the under root away out of the equation and then put it back later on. Okay, now here I'm going to focus, remember, I'm going to focus on only this part of the equation here first. Okay, let's get started. Okay, I have v square peak here, and also there's one thing that I forgot to put over here. When I took the mean over here, mean would mean we are adding all the voltage values over here, but then we have to divide it by the total length, which is t here, right? The total length of the full cycle is t, so I'm gonna have t over here also. Okay, forget that. Now I'm gonna take v square p and t out of the integral, because those are just constant, so I get t over here, correct? Now I have what, so this is t0 cosine square omega t and then dot dt. Now since we can't take the integral of this thing right here, I'm going to convert it into a trigonometric function for which we can take an integral. Remember, your cosine square theta equals to 1 plus cosine 2 theta over 2. Okay, so I'm going to put this into this form right here, where I have v square p over t, and then t here 0. Replace this with this thing right here. Okay, so I have 1 plus cosine 2 omega t, okay, over 2, and then dt. Okay, all right. So also what I could do here, v square peak value square over t, I'm gonna break it into two segments where also I can take 2 out here as a common. So here I would have t0 and then dt, okay, and similarly plus t0 to t cosine of 2 omega t dt. Okay, okay, all right, we're getting close now. So v square p 2 pi 2t, I'm gonna keep it as it is. I know this is going to be equivalent to saying t with limits t0, okay, plus here what's gonna happen, what is the integral of cosine 2 omega t? That would be equivalent to sine 2 omega t, and then the compensation that goes here, 2 omega over here, with limits going from t to 0. Okay, I'm gonna just continue doing over here. So this gets v square peak value square over t 2t. This will be what, t minus 0, so you get t here, okay, and then this plus sign. Okay, now this whole thing, this whole equation right over here will actually be equivalent to 0. How? I can just show you over here real quick. Remember, you have sine 2 omega t here, correct? I can write this equation as 2 omega over t, correct? Right? Because remember, omega is 2 pi over t. Omega can also be written as 2 pi over t. So so this will be 2 pi over t, and then this 2 right here will be over here, 2.2 pi over t, and then t will be replaced by this t over here. So I have this t over here, this t and this t will cancel out, so I will basically have sine 4 pi, right? So this will be sine 4 pi. Sine 4 pi is equivalent to 0, and also when I put this 0 here in the sign, that is also going to be 0, so I get 0 here. Okay, so I can rewrite this equation as v square p over 2t times t, correct? This t and this t will cancel out. Now remember, the square root which I skipped, I'm gonna put that square root back on here, so I get VRMS equals to under root v square p over 2, and I can also rewrite this equation as Vp over under root 2. So if you look at this equation now, Vrms equals to Vp over under root 2 is what we have over here. Okay, so if I go back here to this problem right here, where I knew that here the peak value was 20 volts, I can just simply plug in this value in this equation, Vp over under root 2 Vrms, Vp being 20 volts divided by under root 2, and if I do the math here, I basically get 14.14 volts, which was exactly what we got over here using the graphical method. Okay, so I hope now you understand what average power is, what is the Vrms, and how you can use that Vrms, plugging in this value of Ohm's law to calculate the average power, which represents which is an equivalent to calculating power in a DC circuit. So I hope you enjoyed this tutorial. Thank you for watching. Bye.